see it. Good.
Wait a minute. I have to. Oh.
It's okay. We can see it.
Okay,
so
now you can see it.
Yeah.
So, good evening, everybody. I'm Peter Füri from the Center of Energy Research, Hungary, and I'm modeling absorbed doses from the decay of radon progenies in the nuclei of radiation-sensitive cells of airway epithelium. And why do we have to make calculations for radon in the lung? Because the radon and the decays of its progenies is the main source of ionization ionizing radiation from natural source. And in the lung, unfortunately, the radiation-sensitive cells are near to the surface of the airways, so the emitted alpha progenies from the polonium 218 and 214 may reach them. You know, these alpha particles have a quite short range in water, 40 microns or 60 microns in case of in the alpha of the polonium 214. So most of the time it's not dangerous. Even our skin can protect us. But in the lung, the radiation-sensitive cells are near to the surface of the airways. And it would be an obvious and easy task to measure doses with the instruments. But unfortunately, the lung is a complex structure of asymmetric branching airways. And there is also mucociliary clearance. So it's not a static thing, it's moving. So the radionuclides which are deposited start to move with the moving mucus, and that makes every measurement almost impossible. And in addition, we have to develop such measurements which have enough good resolution to model the very small airways. And according to my knowledge, today there is not an adequate measuring technique to define the doses. So only numerical modeling is possible. So I'm making simulations with a personal computer and just calculating the doses. And how I'm doing this? First, we have a particle deposition model. The stochastic
sorry,
lung
please,
deposition.
can you just say okay in the top there and then bring up the presentation mode so we can see the other slides?
Yes, there is Sekrestes Engedeli, well, whatever, in Hungarian. You press on this. Click.
So you don't see my slides.
We see your first slide. It doesn't
move.
So click away this warning that you opened it from the internet.
It's funny, I don't see it. Wait a minute.
The yellow line, the white box in the yellow line above the first slide.
Sorry, I don't see it. I try it again.
So close and open again. So, okay. But you click away this yellow line where it says Sekrestes something.
Oh. Your streaming is okay. It's funny.
We have some buffer time in the break, so it's
now
okay.
Now you can see it.
Oh.
Do you see it now?
No. Now it's working. Okay. We still see the ribbon, but it works. Good.
Yes,
go
sorry.
ahead.
So as I said, I'm working numerical modeling, and because the lung is quite a complex structure with mucociliary clearance, as you can see on that picture, we can't make measurements and we have to do modeling. So we had to develop a numerical model. And the stochastic lung model provides us the geometry of the airways and the deposited number of particles and the location of deposition. And for my model, in addition to this data, I need also the mucus thickness and mucus velocity and the airway geometry that is provided. And it's provided by the stochastic lung model, and Gabor Albrecht will speak about this. And I have some preliminary results, what I did for some tests. The doses are strongly inhomogeneously distributed in the bronchial airways. So the radiation protection now uses the human respiratory tract model of the ICRP, and it has only a bronchial, a big bronchial, a small bronchial, an acinar, and an exothoracic regions. So only 4 regions. And because the doses are quite inhomogeneous in the airways, I think it's not good to do calculations with such coarse distribution. So I'm doing airway generation number related calculations, and one airway generation number is one bifurcation, as you can see. So one mother tube and 2 daughter tubes. And in my calculations, there are maximally 21 bronchial airways, so I can provide 21 doses. And we have two kinds of progenies: the unattached progenies and the attached progenies. And as you can see, the dose distribution is a bit different for them. And the main goal of my work is to show how the parameters of the subjects, so for the individuals, influence the doses. For example, patients from different age or from different health group or even from different gender can have a different lung, so different amount of radionuclides will deposit there, and the doses will be also different. So according to my first preliminary results, personalized radon lung dosimetry is required to determine the exact biological effect. Yes, and thank you for your attention. I would be happy to answer your questions if you have some.
Okay.